By the end of the 18th century, most physicists thought physics was a well-figured out science, almost close to completion, until the 19th century or early 20th century, when major discrepancies broke out between the theories of time and some observations. This actually gave birth to the whole branch of modern physics. One of such conundrum was the wave-particle duality, which forms one of the many core concepts of quantum mechanics, which is unarguably one of the most successful theories ever formulated. The wave-particle paradox has historically been conceptualized in two forms: the wave-particle duality of light and the wave-particle duality of particles. Now, just what the hell is wave-particle duality? Wave-particle duality is a quantum mechanical principle which proposes that matter could take on either wave or particle-like behavior, depending on the format of observation, which is experimentally counterintuitive but mathematically okay until one tries to give a physical interpretation. For much of the 16th century, Newton's corpuscular theory of light dominated physics thinking. Although wave theories existed at the time, even before then, 4th century philosophers and scientists from Democritus to René Descartes had theorized on the nature of matter using particle or wave properties. Now, technological limitation of time made validating wave theory difficult. So a point in time existed when physicists thought of light as a particle alone, and it worked in explaining reflection and many basic optical principles. Subsequently, diffraction and interference of light was observed. Then it became obvious that corpuscular theory did not answer all the questions. Wave theory had to be considered. In 1801, Thomas Young conducted the famous double slit experiment, which provided an explanation for interference and diffraction effect on basis of wave nature of light. About the same time, James Clerk Maxwell modified the Maxwell equation in a way that conveniently described light as an electromagnetic wave. Although wave theory didn't immediately completely obliterate particle theory, I bet you'd most likely take wave theory if you were a physicist, until problems like the Ultraviolet Catastrophe, Photoelectric Effect, Compton effect, and wave function collapse came along. The ultraviolet catastrophe emerged in the study of black bodies. Classical thermodynamics of the late 19th century would always predict infinite energy density from radiation emitted beyond the blue or violet frequency of the electromagnetic spectrum. The physical interpretation of this was not good. It means matter would radiate all its energy rapidly until absolutely zero, which is only theoretically true. This led Max Planck to propose that electromagnetic energy could only be emitted in discrete unit called quanta, further describing the particle nature of light, contradicting Maxwell's wave theory. This idea allowed accurate description of black body radiation without the ultraviolet catastrophe. This further reinforced the wave-particle paradox. The photoelectric effect is simply the emission of electrons from materials, mostly metals and conductors, when hit by radiation. The effect was observed by numerous physicists, one of them being Heinrich Hertz in 1887. To explain the observation, Einstein hypothesized that light is transferred in packets called photons, an equivalent of Mach's quanta. The electrons could only accept energy in discrete units, as given in his equation E is equal to hf. This also contradicted James Clerk Maxwell's wave model, further deepening the wave-particle paradox. Einstein and a few others won the Nobel Prize for their work on the photoelectric effect. All these, including the Compton effect, was important to the formation of quantum mechanics. But the question now is light a particle, wave, both, or neither? Well, that's probably going to be a personal resolution for any physicist, and we are not even going to attempt answering that. But something we can all agree on is the Schrödinger wave equation. It has successfully described to a large extent all we need to know mathematically without the aforementioned inconsistencies. Studying the mathematics tells us light will most likely be a probability distribution with characteristics which will manifest according to the Heisenberg uncertainty principle. Now, according to Einstein, it seems as though we must use sometimes the one theory and sometimes the other, while at times we must use either. We are faced with a new kind of difficulty. We have two contradictory pictures of reality. Separately, neither of them explain the phenomena of light, but together they do. In 1924, Louis Victor de Broglie suggested that elementary particle could be thought of as a wave. This means particle could have frequencies and wavelength. Later on, Johnson in 1961 repeated Young's double-slit experiment, replacing light beam with electrons instead. The conclusion: electrons produce interference patterns on the photographic film. The results from this experiment accurately verify de Broglie's hypothesis. To conclude, wave-particle duality proposes that elementary particle would exhibit wave or particle characteristics depending on the experiment. I think I can safely say no one understands quantum mechanics. This is a quote from Richard Feynman. Thanks for watching.